Chapter 2 of your Bio 101 class. This one takes a little bit of a turn into chemistry, but again, what we're trying to do is lay the foundation of the terms that you need to know and some general concepts you need to know in order to understand chapters that come afterward. We talked last chapter about what biologists do. They study life. And life is made up of chemicals. Some of those chemicals are considered biological chemicals, some are considered man-made, but we study them and they are the building blocks of atoms that become the building blocks of organelles into cells, etc. So a little bit of information about chemistry. Don't get too bogged down in it. It mostly is understanding what the terms mean in terms of this chapter. It's not really a chemistry class, but understand the terms. We have elements and the periodic table of elements. You probably saw this when you were in high school. There are 92 that occur naturally. We have 112 now because the rest of them between 92 and 112, which I guess is what, 10, 14? My math is not working with when I'm thinking here. That are man-made or made by humans. And with regard to each of the 92, I won't get too far off the mark here. They all have unique properties. So an element is something that is unique to itself. And that uniqueness can be defined by it has a unique melting point, it has a unique boiling point, it might have a unique odor, or it might have a unique feature about itself. And no other element has that. And if you in fact change the element, you may change that particular unique property with regard to the element. All matter is composed of atoms. Atoms are structurally made up of subatomic particles in the nucleus, which is most of the mass of the atom. You have protons, which are positively charged, and neutrons, which have no charge. So nucleus, protons, positively charged, neutrons, no charge. In these orbits around the nucleus, we call them orbits or shells or valence levels. Sometimes those three terms get used interchangeably, although they don't mean exactly the same thing. You find electrons. That's the space that is around the positively charged nucleus, and electrons are negatively charged. So proton, +1 charge, neutron no charge, electron negative charge. Proton has mass, electron has mass, proton has mass, neutron has mass, electron no perceivable mass. And then it shows you where you find them there. So that's kind of a nice little chart there. In terms of these elements, the ones that we study the most, I guess the strongest are carbon, hydrogen, oxygen, and nitrogen. That's because 96% of living organisms by weight are made of just those four. Just those four in different combinations, different amounts, make up 96% of living organisms. Really very interesting. The other 4% are trace minerals, such as probably ones you've heard of, like iron. Some of you may take iron. Some of you may take, probably none of the Earth's zinc. Maybe some of you take zinc. It has become somewhat known. We certainly put, yeah, actually I'll leave it on that in that with regard to trace minerals. These trace minerals tend to be cofactors in different processes that go on in the body, so we don't need them a lot when we have them. Actually, iodine, which is another one that you're probably familiar with, very, very important with regard to the thyroid hormone. And iron is very important in terms of heme. The the compound that actually carries oxygen for you. So two very important trace minerals. In terms of energy, we define that as the capacity to cause change, which is kind of a neat definition of energy. So the ability to cause change is energy, and that not defining that change as positive, negative, or anything. Potential energy, another term, is the energy of matter because of its location or structure. Generally it's determined by its energy level. So if you think back to where you had the nucleus in the middle and then you had the electron orbiting around the nucleus, so the energy level of that particular element or compound or whatever it is you're looking at is based on that electron shell. And actually, generally, not all the time, the further the electron is from the positively charged nucleus, the higher the potential energy. So electrons, those in the outermost shell, which the ones that are the farthest from the nucleus would be the outermost shell, have the most potential energy, and they are the ones that actually cause the bonding and cause the chemical reactions. Its behavior, so chemically its behavior is based on the valence electrons, the electrons that are in the outermost shell, the valence electrons. And here's a slight way that term is different than all the other shells and energy levels, because energy levels and shells really can be used interchangeably, but valence level generally refers to the outermost shell. Elements with full valence shells, so if you have as many positive charged particles as negative, are generally chemically inert. The orbit, and if they're chemically inert, they're very stable. That's the thing about them. If you want them to bond with something new, you actually have to pull one of those electrons off and move it out of there. These orbits are not clear, not 100% defined. They are just the average of where that electron is found, so where it's found 90% of the time. And then electron consists of a specific number of orbitals. Each electron consists of a specific number of orbitals. What happens, what we're looking at here, this ball going down the stairs is trying to illustrate how that electron doesn't stay in one place. It doesn't rest in one place at any one time until it actually gets to the point where it's inert. It has no potential energy, which would be at the bottom. And so the other image here is showing you the outermost valence shell has the highest energy level, and that's where energy is going to be lost first, and then the energy would be lost last, closest to the positively charged nucleus. Atomic symbol, you can see this atomic symbol for carbon. A capital C is the atomic symbol, letter used to identify an element. This was just created. This is a man-made created system. With regard to atomic number, that's the number of protons, and you see that written in the subscript 6, so the lower subscript. And then the atomic mass, remember the atomic mass is the sum total of protons and neutrons, and they tend to be the same unless we're talking about isotopes. So atomic mass would be double that that atomic number, because it's the protons and neutrons together, so it's 12. And this idea of isotopes is you have the same number of protons, but you can have different numbers of neutrons. So neutrons can be forced on or added on. It does tend to make some of these isotopes radioactive. Radioactive and henceforth very useful in medicine, very useful in dating fossils, radioactive isotopes. In terms of matter, matter can come in many different forms. And matter is defined as anything that takes up space and has mass. Matter can consist of chemical elements in pure form and in combinations called compounds. So matter, as I said, is anything that takes up space and mass, but matter can be made up of elements that are bonded together or compounds, which are multiple elements bonded together. So, also matter can take multiple forms. You can have matter as a gas, and you have matter as a liquid, matter as a solid. Something defines it, either its volume if it's fluid volume if it's a liquid, its size if it's a mass, or its volume and space if it's a gas. So element can't be broken down, and compound is a substance that consists of two or more elements in a fixed ratio, such as sodium chloride. A molecule now, and unfortunately sometimes these terms get used interchangeably, but we'll try to keep it clear, consists of two or more atoms held together by a covalent bond. And there are two types of bonds. There's covalent and ionic, and we'll go ahead and talk about covalent right now. So a single covalent bond or single bond is where what happens is two elements will share an electron. So that electron will go around one valence shell, outer valence shell, and then the other outer valence shell. One and then the other. So they're actually sharing it. And that actually is what holds them together in that compound form. And then you can also have double bonds. Two electrons do this particular job. And that's because there are two in their outer valence shell that have potential energy, and you have them going around one orbital or another orbital. The structural formula represents atoms and how they're bound together, so structural formula. And what you have is, in this image, you have your molecular formula first, which is, for example, in hydrogen is H2, and it's a subscript. You have your diagram of the electron distribution, and then the third one over is you have your structural formula, so how those bond. And then the last one is your space filling, because these orbitals, these valence shells, have different spatial arrangements based on which element you have that you're looking at. Basically, three types of bonds. We just talked about covalent. They share. We're going to talk about ionic now. Or I guess we're going to talk about covalent again, I'm sorry. But I will say this: covalent, ionic, and then hydrogen bonding. So let's talk a little bit more about covalent bonds, and then we'll talk about ionic and hydrogen. The atom's attraction for electrons in a covalent bond, the more electronegative an atom is, the more strongly it pulls shared atom towards it. So let me explain that. In what we have here is a water molecule, and the big oxygen in the middle is huge compared to the hydrogens. And I will have to pick this up on the next one because I'm running out of time. I don't know if you guys figured out, I only have 15 minutes on each of these. So we'll pick this up on the next one.